Let's now consider how we represent location and orientation in space. So we will often need to represent things in three-dimensional space, and often we'll have to sketch things out as well as what we mean in terms of what frame is involved and how the point relates to the frame. So one way of doing this is using a perspective sketch. So for example, we can have x-axis along the bottom here going to the right, a z going up, and we represent the y-axis, which is perpendicular to both of these, going into the page. And we could also rotate this axis system round and draw it in a slightly different orientation, in this case with y coming down, x going off to the right, and z coming out of the page. But there's other ways of writing these things down in terms of using an arrow as opposed to trying to draw this thing in a perspective drawing. So let's think about what an arrow looks like. It's got a feather at the back and a point at the front. Okay, so if we're looking at the back and the thing's actually going away from us, going into the page, we'd see this cross at the back of it. So we can represent this then with our original frame as being x going to the right, z going up, and y going into the page, using the back of the arrow showing it's going into the page. Similarly, if we see the arrow from the front, then it's coming at us, so it would be coming out of the page if we see it looking like this, and we can use that in order to represent the fact that here that z is now coming out of the page, y is going down, and x is going off to the left. And actually I prefer that representation because it means there's less lines on the drawing, and it makes it easier when we're drawing things like frames along a robotic device, so we can do analysis for it. What about location of points in space? Well, the important thing to note is we have to do that with respect to a coordinate frame, right? So the point is only defined with respect, the representation of the point is only defined with respect to the coordinate frame. The point in space, is in space, but how we represent it depends on the frame. So typically we have an x, y, z axis system, and they're all perpendicular. We have to define the origin where they cross. And we can then describe the point as being how far we are along the x, how far we are along on the y, and how far we are up the z in this case here. Importantly, when we're drawing our coordinate frames, we should make sure that they obey the right-hand rule, so we don't suddenly, when we're drawing it, we think in another location or orientation, we haven't accidentally flipped an axis. And the way we do this is to use the right-hand rule, where we represent the x-axis with our index finger direction. 90 degrees from that, we have the middle finger pointing along the y-axis, and then the z-axis is represented by the direction of the thumb. Right? So you can either use your hand like that, or build a little tiny frame with X, Y, Z written on it with all the angles set at the right values, so that when you're moving this thing around in space, you don't accidentally flip over a direction, in which case you'll end up getting something wrong. When we're describing positions in space, we have to do, like I said, with respect to a coordinate frame, and we can describe a coordinate frame by something like a value like A. This is frame A, and we describe that within curly brackets. We can then describe a position in space as a vector. In this case, we're saying P is a point, and we're describing it with respect to frame A, so we use the suffix A on it with a little a at the top here. And we notice that this little a basically consists, in this case, because it's a three-dimensional representation of three X, Y, Z elements. We also note we have to specify where the origin of the frame is as well in order to have it well defined, and especially if we need to relate this frame with another frame. The other thing we'll need to relate is, of course, the directions of the bases with other frames. Translation is what we do to move from one point in space to another, which is effectively means we're adding something on to the position. In this case, what we're doing, we're taking a value x, y, z, and we're adding a little bit to the x, a little bit to the y, and a little bit to the z, in which case our addition, our translation in this case is our little dx, dy, dz vector, which is mapping between 2 points in space in 3 dimensions. So this is actually not a linear transformation, it's what's called an affine transformation, because it can be thought of as a linear transformation. In this case, it's not being rotated, so it's just we multiply by, in fact, the identity matrix, and then we add on a shift. We'll talk a lot about this when we actually get onto homogeneous transformations and how we deal with all this kind of thing. We can also think about rotating objects or positions or points in space, and one of the things we have to do then is to define, what are we rotating about, and it's nice if we can pick one of the axes. So in this case, we're going to rotate around the z-axis. One important aspect of rotation is to make sure that you get the direction of the rotation consistent, and the right hand rule is also a good way to do this. We're going to say that the positive direction of the rotation, right, if your thumb is pointing along the axis of rotation, then your fingers curl round in the positive direction of rotation. So this is another important rule that we need to consistently use when we're labeling directions of rotation, and this will be particularly of use when we're actually analysing robotic systems. So that, with the fact that we've already said we have to deal with the frames in a consistent way, here we have to also deal with the actual rotations in a consistent way as well. And if you do those two things, hopefully you won't make any mistakes and we'll get nice consistent results, hopefully first time. So different fields describe rotations in different ways, and one way you can actually describe them is in terms of things like roll. So if you've got an aeroplane, it rolls around one of its axes, it pitches going backwards and forwards, and it also rotates around the other axis. So we've got these roll, pitch and yaw descriptions which are used in different fields, be it aviation or even from image processing and how do you arrange your camera and stuff. So these three angles will give you an orientation basically. The actual conventions though can be different in different fields, so we have to be careful. It won't really matter to us, because what we're going to do with the only thing we're going to use rotations for is rotations around axes of robots, and all we will care about is what the axis is. Is it axis 1, 2, 3 or what have you, and what the direction is. Is it positive or negative in the right hand rule sense? So we won't really worry about this too much. Let's now think about coordinate frames. And a typical problem that we have in robotics is that we're going to get a measurement in one frame and we need to know where the location of something is in the other. So imagine we've got a robotic manipulator and an object and a camera, right? So you could look at this scenario and think, well, actually there's three possible frames here. One of the frames could be the robot frame. In fact, if we're going to use the robot to do something, we definitely need to have the position of the object in the robot frame, because if we know what the position is in the robot frame, we can get the robot to do stuff and manipulate the object by knowing where it is. But it could be also that we could represent position of the object in the object frame. It wouldn't necessarily make much sense to do that because the object is the thing that's moving around. However, certainly another thing which is very likely to happen is that we'll be using a camera, and this is a particular Intel camera that I'm choosing here, which can also tell you the position of things by doing triangulation and all kinds of clever stuff. It can work out where position of objects are in its field of view, but it does it with respect to its coordinate frame, right? So first of all, it's got its direction of X and Y and Z, and it's got its origin, and they're not the same as the origin and the directions of the X, Y and Z for the robotic manipulator. So in order to manipulate this object, we need to know where the object is in its coordinate frame, right? We need to know, in the frame of the robot, what the position of the object is, right? That's what we need to know. If we know that, we can use inverse kinematics to set the joint angles in the robot to get to the object. And then if we know where we want to go, we can also do the same to change the angles and put the object in another location where we want it to be. However, that's not normally what we've got. If we've got a system And it's the same with human vision, right? We're looking with our eyes. Our visual system can work out where things are, but in order to reach out and touch them, we need to transform that information so that our motor system can use it in terms of the frame of the framework of the arm, right? So we've got the position of the object in the frame of the camera, right? That's what we've got, and that's what we need, right? So we need to be able to convert the representation of location in the frame of the camera into the frame of the robot, right? So that's what this business is all about, representing things in different coordinate frames. Here's a very simple example where I'm just going to show you 3 different frames again to make the point one more time. Imagine we've got a point in space. The point stays where it is. It's not changing. But it could be represented, let's say, in frame 2, right? There's one particular representation, and we'll get certain values for x and y in this case because it's only 2-dimensional. It could be that we represent it in coordinate frame 1, which is actually located somewhere else. In this case, the axes directions line up, but they wouldn't necessarily have to. Or it could be even frame 0, and we like to know what the representation in frame 0 is. And mapping between those is not particularly difficult, and something that we're going to now look into a bit more in the next couple of lectures. So why is it important to map between these different frames? Well, I've already said, because we need to care about the frame of the camera and getting it into the representation of the frame of the robot. But we can also use these different multiple frames of reference to analyze robotic arms, to work out where the endpoint is in terms of the frame at the base of the robot. And all we have to do is we say, look, here we've got a 2-link arm. We've got a frame. We can say define the frame at the coordinate base of the robot, and that's the thing we really care about. If we know that, then we're well on the way to working out how to use the thing, and certainly in terms of forward kinematics. So we want to know where the endpoint, right? The endpoint is in the frame at the base. And what we can do is we can define other frames on the way to the endpoint. We can do one at the first joint, and we can do one at the second joint. And we want to know, how do we get then from these frames back to the joint, the frame at the joint at the base. So we need to learn how to do if we can break these things down and be able to transform between frames, we can solve what this is, which is basically the forward kinematics problem. Because what is if I'm saying the frame at the endpoint is frame 2, and that represents the endpoint, what would the coordinates of that point be in frame 2's coordinate frame? So it's quite a simple question. Actually, it would be 0, 0, 0, wouldn't it? It would be 0, because it's at the origin of that frame. So in this case, we're mapping a point at the origin of the coordinate frame of the endpoint. First of all, we map it back to what it is at the joint in the middle, and then we map it back to what it would be in the frame at the base. And we can relate then all of these things to the angles of the joints as well, and that's what forward kinematics is really all about. So there's lots of coordinate frames and mapping between them, which is relatively important to and relevant to robotics. We've already said endpoint of the robot with respect to its origin, but also camera view mapping to the frame of the robot as well. And it could just be that it's not just got a single arm. It might be that we have a robot with lots of dimensionality, and it could be a humanoid robot, and you want to know where the fingers are with respect to the hands, which are with respect to the shoulders, with respect to the eyes. And if it's going to walk around, you might have to know how does that relate also to the framework of the visual system. So there's lots of coordinate systems, and we need to be able to map between them.